Welcome back. So now that you know the project that you're going to be working on is the Rube Goldberg Machine project, let's learn some of the physics content so that you can actually complete that project. So today is going to be kind of intense. I'm going to drop a lot of information on you really fast. However, I have made a tool to help us organize all that information so that it makes more sense. To get that tool, go ahead and pull out your core tools packet. And on the back side, you will find that there is the physics everything sheet. It looks like this. It's page H8. Actually, it's H1 through H8. And if you start at page H1, which is how I would start, because 1 comes before 8, it's right there. Or you could start on page 8 and work your way backwards. Either way is fine. Pull out one of these guys. All right. So now that we've got that, let's get ourselves going. So I'm going to share my screen with you. And there she is. All right. So we're going to start on the physics everything sheet. And let's start. So here's how it works. It's basically a table. It's a cheat sheet that has everything that you could possibly need to know about physics for our class on it. We're going to add a whole bunch of new concepts. Every time during our class we come up with a new concept that we need to learn about, we will add it to our physics everything sheet so that you have that information available to you. So let's start at the very beginning. A very good place to start with time. In the beginning, there was time. So let's just go ahead and zoom in. Our concept at the beginning is time. Time is represented by variable t. We use lowercase t for time. And our definition for time is that it's the sequence or process of events. So how do things happen? When do they happen? You are probably familiar with the concept of time, although it's actually kind of a complex concept. It's a kind of a human created concept. We don't have an equation for time because time is a base unit. It's a base equation. We're going to use it to do other things. In physics, our variable that we're going to use for the unit is seconds, and that's represented by lowercase s. So time in seconds. Obviously, time also comes in minutes and hours, but for physics, we're going to use seconds. No real notes on time. It is what it is. And then at the end, I'd like to encourage you to draw a diagram. So this one actually doesn't have the diagram on it, but there should be a little section here for putting in your picture or image. So I'm going to add in a picture or an image demonstrating it. And in this case, I drew a little clock. That's a good way of representing time. Or I also drew like an arrow going forwards across this line, like the idea that time is moving forwards. It's the sequence of event. This would be like a timeline. Okay. Next, our second variable, our second concept is another base idea, distance. So distance is the amount of space between 2 points. We represent distance with lowercase d. And distance, we're going to give an equation here that distance is equal to 1/2 at squared. That means the distance is equal to half of the acceleration times the time squared. Our base unit is meter for distance. So in physics, we use the meter. And for notes, we're going to use the metric system in physics and really in most of science. So on the metric system, an area that you might remember is that we measure with a meter. You have a meter stick in your lab kit. It's about yay long. There are 100 centimeters in a meter. There are also 1,000 millimeters in a meter. Or if you go the other way, you go up to real big stuff. There are 1,000 meters in a kilometer. A kilometer is about 0.62 miles. If that helps. Meter is like 3.24 feet, 3.26 feet, somewhere like that. And then distance, I drew 2 dots, and I drew the distance between them. Great. Third piece that we're going to add in is the idea of change. So in physics, you will often see a little triangle in front of something. That triangle indicates that there is a change. It's the Greek letter delta, and delta means change. So delta means change in, change in. Ah, I see what that is. Yeah, I know what I'm writing. Delta means it's a change in something. All right. So where would that actually matter? Well, we'd find a change in something if you're comparing two values to each other. So for example, if I use x just for any variable, let's say it's a distance, the distance from point 2 to point 1, or from point 1 to point 2 would be x2 minus x1. X2 minus x1 gives me the change in distance. So the change in x, delta x. Or I could use these little subscripts. So these numbers down low are called subscripts. They're small numbers or letters that go after the variable, and they stand for something. In this case, it's 0.2, 0.1. Or in this case, F and I, F stands for final, and I stands for initial. So the change in x could also be equal to the final value minus the initial value. Because this is a change in something else, the unit for change is going to be the same as whatever the base unit was. So if it was a change in distance, it would be meters. If it was a change in time, it would be seconds. And I put in for notes there, F is equal to final, I is equal to initial, and these are called subscripts. Sub below, script writing, writing below the variable. Cool. I'm going to leave the diagram up to you for that one. You figure out how you want to show change. Next, velocity is our next concept. We represent it using lowercase v. So far makes a lot of sense. And velocity is the rate of covered distance in a direction. So rate means over time, right? How much distance did you cover in how much time? And in a direction indicates that velocity has to have both a magnitude, how big the number is, and a direction, which way are you going? So I might say I'm going 5 meters per second south. That would be a velocity. I have a direction. Or 2 meters per second away from you. Come back. All right, so our equation for velocity. The concept of velocity is the rate of covered distance in a direction. So the velocity is the change of distance, the amount of covered distance, divided by the time, the rate. How far do you go in how much time? So it's delta d, change of distance, divided by delta t, change in time. The unit for that is meters per second. So we do m on top for meters divided by seconds. Obviously, distance is measured in meters. Time is measured in seconds, so meters over seconds. Another way of thinking about velocity is like how fast it is. Generally, we're going to use a positive sign for forwards motion and a negative sign for backwards motion. So the velocity could be either forwards or backwards. It could be positive or negative. The absolute value of speed, hopefully you're familiar with these long straight lines right here on either side of something. That means absolute value, and it means take the total inside and get rid of the positive and negative signs. So if I take the absolute value of velocity, take away the direction, just leave me with the magnitude, that's the speed. So for example, the speed of a runner going around a track might be consistent. The velocity of a runner going around a circle would be always changing because the runner's always changing her direction, right? She keeps changing which way she's facing. And so that would be a change of velocity, but a consistent, constant speed. The direction's changing, but how fast she's running is staying the same. Now we actually have special words for those things. Velocity is what we call a vector quantity. So I'm going to add in that velocity is a vector quantity. A vector means it's an arrow. It can be direction and magnitude. So I'll draw that in, that velocity has a direction, how big is the arrow, and which direction is it going. Speed is a scalar quantity, no direction. The only thing that matters is magnitude. So for that one, it would be the same length of arrow, but without the arrow part. So the same length, but no direction. It doesn't matter which way it goes. All right. So velocity is a vector quantity, speed's a scalar quantity, and if you take the absolute value of the vector, you can find the scalar. Those are some new vocab terms for us. All right. Now, velocity can also change, and when velocity changes, we call it acceleration, and that's going to be the next term that we add. Acceleration is represented by lowercase a, and it is the rate of change of velocity. In human words, we could say this is how much is it speeding up or how much is it slowing down. So the equation for acceleration, because it's the rate of change of velocity, it's going to be the change of velocity divided by the change of time. So I've got delta v over delta t. And now for the unit for acceleration is meters per second squared. Now, this one doesn't initially make a whole lot of sense, right? Where's that second squared coming from? So let me just kind of show you where that comes from. It's time for our favorite part of physics, dividing fractions of variables. Yay! Ah, everybody loves dividing fractions. Okay, so we know that velocity is measured in meters per second from up here. So I'm going to put, for velocity, meters per second. And then it's over time. So that's divided by seconds is the unit of time. So I've got meters per second. Another way of saying meters per second is meters per second squared. And the reason for that is if I'm dividing by a value, it's the same as multiplying by the reciprocal of that value. So I've got meters per second on top times 1 over seconds on the bottom. Multiply the numerators, the tops, meters times 1 is meters. Multiply the bottoms, seconds times seconds equals seconds squared. And then I have meters per second squared. So I'm just taking the unit of velocity, the unit of time, plugging them in their appropriate spots, and ending up with meters per second, or meters per second squared. All right. So for acceleration, another little note to add in is that positive acceleration is going to be speeding up, and negative acceleration is going to be slowing down. Now, I could still have a negative acceleration and be going forwards. If I'm in my car and I hit the brakes, I'm slowing down. I have a negative acceleration, but I'm still moving forwards. If I'm braking, still going forwards. So a negative acceleration doesn't mean you're going backwards. A negative velocity would mean you're going backwards, but a negative acceleration just means you're slowing down. A positive acceleration would just mean you're speeding up. You could be going forwards, you could be going backwards, but if you're going forwards, positive is going to be speeding up. All right. Next piece is we have another fun new Greek letter. And the fun new Greek letter is funny looking E thing. It's actually called sigma. It's the Greek letter for S, and it stands for sum. So the Greek letter sigma here, which looks kind of like a funny E to me, or a sideways M if you prefer. Greek letter sigma stands for sum. And what that means is add everything that comes after that together, or take the total. So add all of the following together. So what does that mean? Sigma x means add up x1 plus x2 plus x3. Add all of the x's together. And you could also write it as sigma x sub n, which would be like add up all the x's. X sub n, n being just the number, any number that comes after x, add them all up. So that'd be all the x's, add them. Okay, so the sum of x's, sigma x. Since this is just adding up the same things, meters plus meters plus meters gives me meters. So my unit would be the same as my base unit, and no real notes for that one. All right. We've already talked about acceleration, but let's talk a little bit about acceleration due to gravity. So acceleration due to gravity can be represented by a subscript g. So this is a little tiny subscript g here. It's not ag, it's lowercase a subscript g, which means acceleration due to gravity. Or I could just use lowercase g. You'll see it written both ways. It stands for acceleration due to gravity. And I noticed that I missed an E there, acceleration due to gravity. So the acceleration due to gravity is the acceleration of all objects in a gravitational field due to the force of gravity. So we know that everything accelerates if you're in a gravitational field. On the Earth, that goes down. So for falling objects, I have a couple of different equations for falling objects. These are just a manipulation of the other equations that I gave above. The first one is that I can find the velocity of a falling object. Velocity is equal to acceleration due to gravity times time, or V equals gt. I could also write that, since I know the other equation is that V equals a sub g times t. Velocity is equal to acceleration times time. Another one is I can solve for distance. Distance is equal to 1/2 gt squared. You'll notice this is the same equation that was given up above for distance, right up here at the top of the screen. Distance equals 1/2 at squared. All I've done is I've subbed out acceleration for acceleration due to gravity. So distance equals 1/2 gt squared. It's just acceleration due to gravity, another way of phrasing it. So I could write it again. Distance equals acceleration due to gravity. Oops, I forgot my 1/2. Distance equals 1/2 acceleration due to gravity times squared. Okay, on the Earth, we have a consistent acceleration due to gravity because the Earth's mass stays the same size, and your distance from the center of it is always the distance from the center of the Earth out to the crust of the Earth, or the edge of the Earth. And because those are the same, we know that the acceleration on the surface of the Earth is always 9.8 meters per second squared. Sometimes we'll round that to 10 meters per second squared, but 9.8 meters per second squared is more precise. So that's about 10 meters per second squared, but we'll use 9.8 when we can. All right. Two more for this page. So one more is mass. Mass is another base unit. We use lowercase m to represent mass, and mass is the amount of matter in an object. So that's how much stuff is there. That includes both the number of atoms, number of molecules, and the size of those molecules or atoms. It's just how much total stuff makes up that thing. There is no equation for mass. It's a base unit that we'll use in others, but we, in physics, use the unit kilograms. Sorry, there's no equation. So kilograms we represent as kg. In your other science classes, you might know that the base unit for mass is g, grams, but for physics, we always use kilograms because, as you'll find out in the next one, it's really helpful for force to have kilograms there. So we're gonna use kg, kilograms as our standard. As mentioned, grams is the base unit for mass. So 1,000 grams make up 1 kilogram. And one other note is that weight is not the same as mass. Weight is a force. So weight is the force of gravity on a mass. Another way of writing that is that weight is the mass of the object times the acceleration due to gravity. So weight is the force times the acceleration. Weight is a force downwards. Because if you go out to space, you have the same mass, right? You haven't changed, but now you're floating out in space. So you don't have any weight. Your weight can change by going to different planets or putting yourself in different gravitational fields. Your mass is how much stuff is there. So you can change your mass by eating something, but you can't change. Yeah, you can change your weight that way too, because we're on the Earth. Never mind, we're good. Okay, last one for this page, and that will finish up page 1. The last one for this page is force. Force we represent with capital F. It's the good kind of capital F. And a force is a push or pull on an object that causes a change in motion. It can cause a change in motion. So it doesn't have to cause a change in motion. You could have a force on an object and it's just sitting still, but it can cause a change in motion. So I'm just going to add in can. Doesn't have to, but it's a push or pull on an object. Our equation for force. Force is equal to mass times acceleration, or F equals ma. This is a big one. We're going to use this a lot. So F equals ma, force equals a mass times acceleration. And the unit of force is the Newton, and we represent that with a capital N. Newtons are equal to kilograms times meters divided by seconds squared. So if you look at the unit for mass, we had F equals ma, and then if I look at my units, mass is in kilograms, acceleration is in meters per second squared, kilograms times meters, all of it divided by seconds squared gives me kilograms meters per second squared, and I call that a Newton. Cool. Just to give you a scale of like how big a Newton is, a Newton is approximately 1/5 or 1/4.5 of a pound. So 4.5 newtons make up 1 pound. So my weight in pounds would be on the surface of the Earth is about 145 pounds. If I take 145 and multiply it by 4.5, let's say 150 times 4 would be 600. 140 times 5 would be 700. So I'm somewhere between 600 and 700 newtons. Let's say 625 newtons. I would actually use a calculator and calculate it for real. But I'm somewhere in that zone. So a human could be in the many hundreds of newtons of force, of weight. Okay. I'm in the 600 to 700 Newton range. All right. And we're going to come back. This little squiggly line means proportional to. So we're going to talk about proportional and directly and inversely proportional. And we're going to do that by taking a look at our new piece, which is our Newton's laws. Where'd y'all go, Newton's laws? Just had you. I apologize for that delay. I had them all pulled up and they've run away on me. Ah, there they are. Okay, sorry about that. All right, so here are Newton's laws. So we're going to run through and we're going to add this in on page 2 of your notebook. So this is going to go in at page 2 of your science notebook. If you want to pull out your science notebook like this and flip it open to page 2. Page 1 was the Intro to Physics and Engineering. Page 2 will be your Newton's laws. And you can absolutely use the back sides of things. So please make page 2 the back side of page 1 if you feel comfortable doing that. Save some paper. All right, so I would assume that you've probably heard the story of Sir Isaac Newton. Sir Isaac Newton was, I don't know, somebody who lived hundreds of years ago. the cute story is that he was sitting under an apple tree, and an apple fell down from the tree and hit him on the head, and he was like, "Oh, I've got it! Gravity! I understand gravity." It's a really cute story. Unfortunately, it's like total crap. That's not how scientific discoveries work. What actually happened was Sir Isaac Newton took measurements of the stars and planets and really detailed notes over the course of like 5 to 10 years. And then by looking at all of that, he was like, there's something going on here where the planets are moving really consistently. And the only thing that could be making them do that is if they were being pulled towards the sun and orbiting around the sun. And I don't know how the heck that happens, but let's call it gravity. It's this force holding things together. Okay. So he came up with 3 laws, and we're going to talk through Newton's 3 laws of force. So the first of Newton's laws is inertia. The idea of inertia says that an object in motion remains in motion and an object at rest remains at rest, as long as there is no outside force acting on it. So an object in motion remains in motion. So if I put something in motion, like these keys, which I'm holding here, if I put it in motion on my desk, let's take a look. There they are. You see them? Good. Okay. And I'm going to put them in motion and see if they remain in motion. Uh-oh. I pushed them, but they didn't keep going forever. They stopped. Huh. Well, that's a problem. So an object in motion should remain in motion unless it's acted upon by an outside force. So what outside force was acting upon those keys? Turns out it was acted upon by the force of gravity and the force of friction of the tabletop pushing back against it. So the force of friction stops these keys from moving forever. If I took them out into space, where there is absolutely nothing around, no other forces, no other friction, and I pushed on the keys, they would go out into space and they would keep traveling into space forever. Same direction, straight line, all the way out. So an object in motion remains in motion, an object at rest remains in rest, unless acted upon an outside force. So another way of saying unless acted upon by an outside force is by saying that's true if the net force is equal to 0. Or another way of phrasing that is if the sum of all forces equals 0. So as long as all the forces balance out, an object will keep doing whatever it was doing, sitting still or going. All right, Newton's second law is that force is equal to mass times acceleration. It's actually phrased as a proportionality. So let's talk about what a proportionality means. A proportionality, so the Newton's second law says acceleration is directly proportional to force and inversely proportional to the mass of the object. So directly proportional means if one thing goes up, the other thing also goes up. So if my acceleration, or if my force increases, my acceleration will also increase, which makes some sense. If I take my keys again, there we go, and I put, where are they? There. And I put a small force on them, the acceleration will be small and they won't speed up too much. That was a small speed up. But if I put a big force on my keys, like I'm gonna hit them real hard with my hand, ooh, they accelerated really fast. Let's try that again. Small force, big force. The harder I hit them, the faster they accelerate and speed up. Okay, so that's a direct proportionality. And a direct proportionality happens when they are on opposite sides of an equation, opposite sides of an equal sign. In this case, force is on one side, acceleration is on the other side. if I increase the force, the acceleration will also increase, because if this side gets bigger, this side has to get bigger. The other part is that the acceleration is inversely proportional to mass. Inversely proportional means if one thing gets bigger, the other thing gets smaller. So if my mass gets really big, my acceleration is going to end up getting smaller. And I show that by putting the mass on the underside of the equation. So it's under in the denominator down here. 1 over the mass, if I do 1 over 1, I get 1. 1 over 2 gives me a half. 1 over a million gives me 1/1,000,000th, which is very, very, very small. So the bigger this number gets, the smaller the answer becomes. So mass and acceleration are inversely proportional. Another way of showing that is let's do things that are different masses. So I'm going to put the same force each time. All right, here are my keys, and I'm going to put a big force on my keys. Thwack! And they accelerate and move pretty fast. But if I do the same thing, here's a stool down below. I'm going to put the same force on this stool. Whack! It barely accelerates at all. It did a very slow, small move, not much acceleration. Okay, so the bigger the mass, the less acceleration. The bigger the force, the more acceleration. We call those directly proportional and inversely proportional. And those are going to be really key ideas that keep coming up over and over again. Or looked at another way, if I have to keep force the same and the mass gets multiplied by 100, so that my mass is 100 times bigger, or sorry, my acceleration is 100 times bigger, then my mass would have to be 100 times smaller. So if my mass gets 100 times bigger, my acceleration is going to be 100 times less. Flip-flop, inverse. Good. Okay. Newton's third law states that every force has an equal and opposite force. So if I push on the wall pushes back on me. Shown vertically, currently I am sitting here in the stool. The force of gravity is pushing me down onto the stool. But I'm not falling into the ground. I'm staying still. So if I'm staying still, every force down has to have an equal force up. So the force of gravity is being balanced by the force of the chair. So the force of the chair is up, the force of gravity is down, they balance each other out. And this upwards force that's equal to the force of gravity down, we also call that the normal force. It means perpendicular. Normal is perpendicular. So perpendicular would be like to the surface of the chair. The surface of the chair is here. The force of normal is up. It's pushing me back up. Looked at another way, if every force has an equal and opposite force, if I punch the wall is going to punch back equally hard. So if I go, ah, and slam my fist, did you see that? And slam my fist into the board might get dented, but I also might break my hand. Okay? So I put a force on the wall. If I put a little force on the wall, like this, beep, beep, I feel it on my finger, but it's not going to do a ton of damage. If I give it a big slap, ow, that was maybe not a great idea. All right, so those are Newton's 3 laws. So we now have filled in the first page of your Physics Everything sheet. We have talked about Newton's 3 laws. So you've got your first page of Physics Everything done. You've got page 2 of your notebook done. And then we are going to come back and talk a little bit more about the second set of things from your Physics Everything sheet. Excellent work. Whew, here we go.